Hi guys, today we will talk about the boost in DCM with a little bit of design and also a simulation. But first, as always, let's explain a bit the physics. So as you can see, the boost converter, as always, it has the inductor connected with the input, and here it has the MOSFET, and here the diode, and of course the capacitors and stuff. Now, why the boost? Now, why we want to design the boost in DCM? There are several reasons. The first reason is because into DCM, especially in the low power, is very convenient for efficiency, for EMI, and also for better control. CCM is harder for the right pole, for the right hand plane story, and you most of the time the boost converter you don't want to design in CCM unless there is high power to request it. But when you have to design in low power stages, like for instance 120 watt or even 240 watt, a boost DCM multi-channel can be your decision. Of course, you have to put more in parallel to make it more efficient, but the advantages of the DCM are also that the inductor shape of the current is just a linear straight line like this. And from this waveform, you can basically study everything that you need. So, what is happening here? Basically, oh no. So basically, this is the switching node. The switching node can be high or low. Okay, between V out and 0. Now, when the switching node is off, is 0, it means that the MOSFET is conducting. When the MOSFET is conducting, we can represent it like a short. So the circuit here in this case is just this, and the inductor is charging. In the other interval instead, the MOSFET is open and there is a direct transfer between the input and the output. In particular, the energy of the inductor is flowing to the capacitor. So, we could spend hours in designing this circuit, okay, really hours to make a perfect design, but there is a way to design it very quickly. The trick is to exploit as much as possible the physics of the inductor. So you see that this is a straight line, right? So, and the peak of the inductor is the same peak for the MOSFET, is the same peak for the diode, and etc. And every parameter basically revolves around the T on. If you have the T on, you can easily calculate the T off, which is this one. And when the T on plus the T off is less than 1, you are into DCM condition. And how can you calculate T on? Is pretty easy. You know that at each cycle, the energy of the inductor is 1/2 times L times I peak square. Okay? Now, you know the relation between the energy and the power, so the power is equal to 1/2 L times E peak times the switching frequency. So you can easily calculate the T on out of the power, and after some calculation, you can see that the T on is equal to 2 times L times the output power over V in square times the switching frequency. V in square you can put it outside, and you can easily calculate everything else. Now, you can also from the T on, you can also calculate other formulas like the T off for the verification of the DCM condition, and the T off of the DCM is basically it recalls similarly the CCM duty cycle. So it's basically like V in over VO minus V in times T on. And of course, this condition has to be true. From this formula, then you can from the T on you can calculate the peak of the inductor, and you can select the components. You can make a very fast designing just by keeping everything constant except the L and the output, so except the L and the switching frequency. You can adjust by thumb your design and make a simulation out of it if you want to make a very quick design. For this reason, I open an Excel. So here you can see that there are already V in, Vmax, Pout, VO, and EO. This red one are the specification, and we cannot touch it. The funny thing that you can do on Excel is to name each cell with a specific name. For instance, you can name this cell as L and this cell as F switch. How? Just click on this cell and write your name, like K. For instance, you want also milliohm, then milliohm is equal to 1 times 10 to the minus 3, and this cell will become M. Okay, very easy. So if I see, if for instance I write L times U, I will have the value of the inductor, which is 3.3 times 0.6. Okay, time to the minus 6. Okay, very easy. Also to debug, very easy. Because otherwise you will have formulas like this, F8 times this, times this, times this, over this. What is this formula? Nobody knows. Not even you. Okay? So, we can calculate the T on, which is the key parameter of this guy, and then we can make a very fast simulation on LTspice to verify it. So T on is equal to radical square, which is radicu in Italian or SQT in English, times 2 times L times U. You see, it's very easy to write it, times PO times, let us see, times PO times 1 over let's put the V in 1 over V in times radicu, okay, times PO, which is easier, over the switching frequency. Of course, we need the K. Remember to put the K or to put the milli easily, because of course, otherwise I have to put this on parentheses, but you get the point. Or if you want really to be safe, you could put this guy on parentheses, okay, and just write K. But it's the same. I mean, it's basic math. So this is our T-on guy, okay? According to the SPICE simulation, is 2.2 times minus 6. Interesting. Okay, interesting. Then we can also suppose that we have also a number of channels, okay, which basically will reduce the power at each channel, okay? So if that's the case, we suppose that we use, I don't know, we can try to use 4 channels, so we will have 4 boosts in parallel. We can see that this power then gets divided by 4, for instance, by the number of channels, okay? Again, this number of channel we'll call n, okay, which is the number of channel, and so we have the power divided by n. This will be the parallel channel that we have. Okay, so and of course we can also put the power per channel. Probably it's better to do like this. PO per channel. It's of course PO over n. Okay, interesting. Then of course we have to calculate the T off. We calculate that the T off, which is V in minus VO minus V in times T on. The T off is equal then to this formula here. V in minus V in. Oh, sorry. Okay, it is equal to V in over VO minus V in times T on. Of course, I forgot to name the T on, but you got the picture. So So basically, we call this one T on, as we did it before, and we call this times T on. Okay, now let's verify that the condition, of course, is less than 1. So this one is T off. Let's see that the condition is that T on plus T off. But of course, we have to compare it this time. This T on and T off time has to be compared with the total time. Okay. So T on plus T off plus T dead is equal to 1. Or else we can write, probably more easier to understand, that because T on plus T off, of course, we need to transform it in duty cycle. Otherwise you cannot. Otherwise you cannot verify it. Otherwise you cannot verify it just with the T on and the T off. So we need. So we need also the TS, of course, which is 1 over the switching frequency. Yeah, of course, 1 over the switching frequency, which is the switching frequency is 10 times k. Okay, and so of course T on plus T off must be less than the entire switching frequency, than the entire switching period. So the condition is that T on plus T off minus TS has to be negative, or better is this minus T on minus T off has to be positive. Wait a second. TS is equal to T on plus T off plus T dead. All this sum has to be equal to 1. Has to be to 1. Sorry, it has to be equal to the TS. So T on plus T off. Yes, of course it's negative. Wait. Let me take another. Let me do a bit of demonstration here. So we said that TS is 1 over the switching frequency. Okay. T off is equal to V in minus V out minus V in per T on, and the duty cycle. So we don't have to fall into CCM. So the CCM condition was that the duty cycle is equal to 1 minus V in minus V out. If you fall in this condition, you are in CCM, okay? So you have to stay away from this condition. So, which means that the duty cycle has to be less than 1 minus V in minus VO. Which means that, okay, here we have T off, and here we have T on. So from this formula, we can write that T on, we can move all the other terms to the other side. So T on times 1 plus V in over V in over VO minus V in has to be less than 1 over the switching frequency. Yeah, because this is easier to understand. So okay, this is way better. So let's write condition Tion times 1 plus Vin over Vo minus Vin Tion Tioff. Yeah. What's the problem? Yeah. Why don't you calculate? Ah, yeah, because I have to close the... Okay. And this has to be less than the TS. 1 over F switch, which is basically TS. This is basically less than TS. Okay. So TS is equal to, and TS has to be higher than this. So TS is 1 over the switching frequency times K. And it is. Because if you do this guy minus this guy, you have... Ah, no, it's not. No, apparently it's not. Okay, so we are not, so in this condition, we are in this condition of power, and in this condition of stuff, we are not in DCM. Which means that we either have to lower the switching frequency a bit. You see? Yeah, we can just lower the switching frequency to 60 kilohertz, 70 kilohertz or something. Or we can increase it in the number of channels. Yeah, for instance. So now we have 6 channels, 20, because to stay in DCM, the inductor has to be very low, like 2.8, like 1, okay? It has to be very low. And as you can see, the power also has to be very low. That's why I put a lot of channels. Now we can switch on LTspice. In LTspice, of course, what you need to do is to put the input voltage and the inductor. We will put the 3.3 micro. Okay. So let's suppose that we focus on 6 channels and the power of channels is 20. It means that on the output side, we will have a current of how much? If the input volt, if the current is equal to, we have 24 120 over 24 divided by 6. Okay, 0. Okay, very easy. Just write it here. The upper channel is equal to, of course, 0.83, just in case to make it visible. So we will use 0.83. Of course, there is no need to simulate each channels. This one is enough. Just put 100 micro to simplicity. Just put the N MOSFET. Okay, the first of the list will be enough. And just put the diode. The first of the list will be enough. Okay. Schottky will be enough. Okay. This is just to simulate to simulate that the circuit is exactly in DCM. And of course, I forgot just to tell you that we can verify also the peak. The peak is also very important because you can calculate everything from the peak. So the peak is just a square. It can be calculated. From the Tion, which is the best way, I think. Yeah, because otherwise we would have to explicitly write everything all over again, which I don't want to do that. And so let's just write that the peak is equal to it's just a straight line, so we write just V in times T on over the inductor L. Yeah, something like that. So the input voltage times T on over the L, of course. V in, forgot to do that. V in times T on over U times L, okay? Yeah, this is a reasonable peak. This is a reasonable peak. And of course, no, but you're not using the power. I'm using the power because everything inside T on. In T on, you see there is PO over N, the switching frequency, L, there is everything in V on. The input voltage, everything. Everything. Okay? So everything is in here. Okay, so the peak is 12.13 in this condition. Let's see immediately. Let's use now in this stage we can use this one. Then I will make a proper design for the turn on. So between the pulse, it will be between 0 and 15. Okay, rise 1 nano, and T on will be, of course. We don't know. We don't know the duty cycle. I suppose the duty cycle will be around 0.7 or something. Let's just write d times d times d over the switching frequency for now, and the period 1 over the switching frequency. We can just make a sort of guessing. Of course, in real life there will be a control for this. Let's write out, okay, and dot param d equal to, I believe that 0.7 could be a starting point, and the switching frequency to 100 kilo, 80 kilohertz, was it? 80 kilohertz, was it? Was it 80 kilohertz? 80 kilohertz. 3.3, 80 kilohertz, 0.7. Let's see. In 1 milliseconds, where do we arrive? The output voltage should be around 24 volts, okay? Okay, here it is around 19, so we need to increase a bit the duty cycle. I would increase to 7.75. Okay, we are at 22. It's incredibly fast. I like it. 78. Let's see. Okay, now we are at 25. You see, it's faster in this way. 76 probably. Okay, we are in an acceptable input. Acceptable output voltage. Oh no, I am really unlucky this time. And now we can verify. We can verify all the datas. So I said that the input, the peak current is 12. Now let's see if I am a scammer or my calculation proved right. So let's see. Woohoo! We are at 11.50. Okay. Wait. Please don't kill me yet. Don't kill me yet. Wait. I calculated the 12.13. Okay, in my defense, I can say that it's not exactly 24 volts. So probably we can do just a little bit better. Like this, probably. Yes. And we have 11.7. Yeah, let's see that LTspice also simulates some parasitics effect and stuff. And as you can see also, here we have a very small T off. Let's verify that the T on is similar. So it should be basically 10 microseconds. Let's see if it is true. Okay, how much here we have? Guys, we have 9.61 microseconds. I mean, the calculations are proving almost real. So let's write T on spice it's 9.7 microseconds, and the T of spice is 1.8 microseconds. Here is basically 10. So we have a reasonable discrepancy, I say. T of spice is 1.8 times U. 1.8 times U. And this is 9.7 times U. So, guys, I think that we have at least a relative mistake, a relative error, I guess that it's very low, okay? Come on. What is this? Ah, thank you. Yeah, times 100 probably. Guys, 4%. I mean, it's not bad. Okay, it's not bad. It's not far from the reality. Eh. So it means that this quick design proved to be reasonable. Okay, at least that now we have something to work on. Now the problem is that, as you can see here in the output voltage, if I replace this guy, this guy is not starting from 0. You see, he's starting from 3.6. It's not a random because you have the direct connection between the input and the output. This is a huge problem in the boost converter. So normally you have to add another switch in series here to detach it, because otherwise you cannot handle short circuit. Okay. Okay, so and now this is the basic, and now this is the basic for the boost converter. Maybe in the next video I will start from this boost converter with this kind of calculation to also design the control in the analog control for boost DCM. A little bit of designing of a type 2 PI, and then we can see how it reacts on a step load. Okay? Thank you guys, and see you in the next video.